So today we looking into the energy, into the mechanical energy. First of all, you know that there are three types of mechanical energy. There is kinetic energy, mv squared on 2. There is gravitational potential energy, which equal mgh, and there is elastic potential energy, kx, where x is extension of, if we have a spring which we stretch or compress, then x will be changing the length of the spring, and k is the spring constant, which is defined by from the constant f equals kx. Gravitational potential, elastic potential. Now, when we're looking mgh, we cannot find what is the gravitational potential energy until we do what? We decide where r is 0. Because if it's height about what? Let's say this has mass of 100 grams, or 0.1 kilogram. Let's take G 10 to make it more simple, and height of the table is 1 meter. What will be the gravitational potential energy of this? It has mass 0.1 kilogram. Take G10, and we take, and height of the table is 1 meter. What is the gravitational potential energy of this thing on the table? What will be gravitational potential energy of this matter on the table?
0.
You're saying 1? Is it? And you both must be right. Because we need to decide where we take 0. If you say relative to the floor, it will be 1. Relative to the table, it will be 0. Because what is height above the floor? 1 meter.
-1.
And you calculate 1. But what the height relative to the table?
Is it negative energy?
If you ask what is gravitational potential energy relative to the ceiling, let's say it's 2 meters, then it will be negative 2 joules. What does it mean, negative gravitational potential energy? To do that, we need to recall what is energy in general. What is energy? Can someone answer the question, what is energy?
Work.
Ability to do work. Energy, if something has energy, means it has ability to do work. Let's recall from the last year, what is mechanical work? What is mechanical work? Force times displacement times cos angle between them. When we have object, we have force at the angle of the display to the displacement. That's mechanical work. Fs cos theta. And also, if we work done, it's change energy of the system. So work equal change of the energy. And it could be 2 cases. We can do energy on the object, on the system, or object can do work. So for this one, to get to the ceiling, will it get there by itself?
No, you need
No,
to put into
we need to do work to get it there. That's why it will be negative, because to get there we need to put energy in. But that's negative can be only with gravitational potential, because where we take 0 height can change. We can take it a different.
What if you pull a string out further?
With the spring, it has, if you have a spring, if it has length, it has unstretched, so an unstretched length. F spring. It has an unstretched length. And so it has 0 elastic potential energy in it. So when I stretch it, it will be, I'm increasing the change in length, I'm giving it more and more elastic potential and energy. We cannot get negative.
What if you can somehow squish it smaller?
If no, this one cannot squish, if there's another one that we can, I don't have this one. Take this one. So this one, I can, so now it has zero gravitational, elastic potential energy. When I push, I'm doing work. So I'm increasing its potential energy. And when I release it, it can do work, it can push something. Both positive. When I stretch it, I release it, it can do work.
Square.
So with this one, it's squared. Whatever is changing length, can make shorter, longer, it's still positive. It's only with gravitational potential can be negative.
But if you're showing calculations, would you need to say x is a negative?
Doesn't matter.
Doesn't matter.
I believe we remember something for maths.
And we have that total energy of the closed system is constant. So what does it mean, closed system? There is no energy input to the system and no energy coming out of the system. So total energy will be constant. Kinetic energy plus elastic potential plus gravitational potential energy will be constant. And the best way to understand how it works, let's consider oscillation of the mass on the spring. If you will connect mass to the spring and pull the spring and let it oscillate, if I will add mass, if I will drop it, it will start to oscillate up and down. And let's consider what the energy transformation happens through this process when the mass oscillated on the spring. That is like every year after year, questions related to that comes up on the exam, and year after year, students get trouble. So, let's say we have a spring with a spring constant K, and then we add mass and we drop it. That's important, because there is a difference, we drop or we just lower it. What will be the difference between we drop it or we just lower it? What will be the difference?
Speed.
When we drop, do we do work on it? No. But when we, it's gravity do, but when we just, so when we drop, one thing, when we just lower it with the hand, we apply force all the time by the hand, so we can do work. So it's not the same situation. So consider we just drop it. And it goes to here, let's say, and that will be, let's say, x, how far it goes. And then it starts oscillates between these two positions, top and the bottom. First, let's consider forces acting. We have, at any point, we have two forces acting. We have mg and we have kx, or elastic force, F equal kx. G changes through the motion. No, mass doesn't change, gravity doesn't change. But x changing, so we have the net force changing all the time. And initially, and this, let's say, is a midpoint. This is a midpoint. And that will be point where, if we just gently lower it, where it will be tangent. Not oscillate, just tangent. What we can say about mg and kx at this instance? They're equal because it's in the equilibrium. So in the middle we have f net equals 0, mg equals kx. What happens when it's above that line? Which bigger? mg bigger. X here is 0, then it's increasing, increasing, increasing. Here we have f net is down. So we have mg greater than kx until it's stretched enough. Initially mg greater than kx. So because net force is 0 here, acceleration in the middle is 0. So it's accelerating down from the top to the middle. And then we have, when it's past the midpoint, we'll have the f net will be up. We'll have mg will be less than kx. So we have here acceleration down. Here we have acceleration up because kx greater than mg. So it's slowing down. So where will be the maximum velocity?
Middle.
In the middle. Where acceleration is 0, velocity will be maximum. What will be its velocity at very... What is its velocity at the very top and very bottom?
0.
0. So we have v equals 0. V equals 0.
Crazy.
Does that make sense? How the forces and accelerations and velocity changes through this motion of the mass on the spring. Make sense?
Yeah.
Now let's say what happens with the energies. Let's take the energy at the bottom, take gravitational potential 0. So what is energy initial? What energy it has initial? What type of energy?
Gravitational potential.
So here we have all energy is just gravitational potential will equal mg x, because we take that this is x. At the very bottom, what energy it has?
Elastic.
Elastic. All energy will be elastic, spring stretched. Gravitational 0, speed 0, so at the bottom all energy equal elastic potential equal kx squared on 2.
Why is it elastic potential energy? Why is it not just elastic energy?
Because it's potential energy. Potential energy, kinetic energy that relates to the motion.
Yeah.
When something moving. This stretched spring is not moving, but it's not doing any work now, but it has potential. If I release it, it can do some work. That's why it's elastic potential energy. And we will learn later on about electric potential energy down the track when we learn about electric field. And in the middle, it will have all three energies. So energy it will have some gravitational potential, some kinetic, and some elastic potential. But total energy will stay the same. It just, at the top, just gravitational potential, then had all three up to the very bottom, where it all will be potential. If you sketch the graphs of the energy regarding against x, the total energy stay the same. Does not change. The what will happen with gravitational potential? It is initially where the x is at maximum. Gravitational potential is at maximum. When we get to 0, it's 0. So that will be green is gravitational potential energy.
Wouldn't it go from the top down?
X is 0. If you take this as 0.
Yeah, but are we dropping it from the top?
No, we're dropping, but we take x equals 0 here at the bottom.
Oh,
X equals 0 at the bottom.
okay.
So that means when x is 0, no gravitational potential.
So that line up the top is the total energy.
This is the total energy, which stay the same. Now, what will be the kinetic energy? How the graph looks like of the kinetic energy against x? What do you-
It peaks
The quadratic.
in the middle. It's a quadratic.
It has to be 0 at the bottom and at the top,
Zero.
and then and maximum in the middle.
Yeah, yeah. It's a parabola.
So it will be some sort of the parabola.
Does anyone have a
But it never will be equal total energy, because there will be no case here when it's only kinetic energy.
Yeah.
So it will be something like this. How the elastic potential energy will be. We have mathematical formula for it. Kx,
Yeah.
this is pure parabola. And the bigger, when x, we have, when x is 0, it's stretched at its max. So it's biggest. When x is max, we take x as a height. So it will be, when x is 0, it's maximum, and then going down, so that will be something, at this point, it's 0, and here it's equal. That will be the elastic potential. But at every point, all three of them should add up to the total energy.
And red is kinetic, right?
Red is kinetic, yes. This is kinetic energy. And this is elastic potential energy. So that's how the forces, accelerations, velocities, and energies changes through this. That's the theory. Now let's have a look through some examples.